Our next step in the study of multivariate functions, or two-input functions in this particular case, is to look at how we would graph or imagine the shapes of the graphs of these functions. If we think back to a single variable, we've been using graphs all the way through. This is nothing new. Ever since you've seen functions, you've been working with graphs. Now keep in mind how we built those so we can generalize to two inputs. What we'd have was y equals a function of x, and we would end up with a graph in x versus y, and we have the graph do whatever it does. F of x is our y value. So for each x value, we have a single y value. In terms of nomenclature around this, we would say that we graph this function. The function is the green line, but we graph it on a plane, the xy plane, or what's often called R2. For the real line squared, we have two real lines, one in the x direction, one in the y direction. And the reason for that is that we need one dimension for the input and one dimension for the output, or two dimensions for the relationship between those two features. Now, of course, if we go to our new models where we have two variable functions, well, we need two dimensions for the two input variables, and there's only one output, so we need one more dimension for that. And of course, that means we need three dimensions as the space to show the relationship between the inputs and outputs. There we go. And so what we're going to do is define the graph of a function of two variables as a set of points again, but they're going to be a set of x, y, and z points. And so g of x, y gives us a single z value. Now, that's going to be called R3. I'm not sure that's how you spell R as a word, but R3. That's going to be three axes, an x-axis, a y-axis, and a z-axis. And we typically view this as our usual three-dimensional world. What would this look like in three dimensions then? Well, a typical graph of a function of two variables is going to be a surface. And here's a picture here. We imagine just like looking out on a field or something, or on a hillside, we're going to see a surface. And the idea is that at any xy coordinate, we are going to be able to go up to the matching z value on the surface. So the z can be computed if we know the x and y location that we're at. And notice when we're sketching in three dimensions, we typically only show the positive direction axes. Otherwise, it gets too confusing to draw three dimensions in two dimensions. And even then, we're going to see it's pretty cryptic. So just keep in mind that we're going to show the positive x direction, positive y direction, and typically we think of x as either is out towards us. And this one is often drawn as to the right. We'll typically do that when we look at graphs in a moment. And z is up. Positive z is the up direction. So we have a surface. If we pick a point on a map, is one way to think about it too. We have a map that's x and y, and if I go to a location on the map, then I get a certain height of a hill or a certain temperature, if we go back to our earlier examples. And if I know my x and y, I know this output value. In terms of the graph, we usually think of it as a height, that third output value. All right. So then how do we draw this? Well, we sketch out with the xy axes and order them in this way. It's called a right-hand system. You can read about that in the text. Let's take an example here, a very simple example, where we simply set z, or the function, equal to the constant 5. So z is constant and equal to 5 everywhere, or at any x and y point. Well, what does that mean? Well, it means when we go up to sketching our graph, we can count up in our z direction up to 5, and then what we're going to do is get a plane, a flat plane, that's always equal to height 5. It's always at height 5. If it was at height 4, it'd be moving down. If it was height 6, it would be moving up, but it's always height 5, everywhere regardless of what x and y are here. So the fact that x and y are missing is not a problem. It just means that, oh, you give me a point, any point you like, the height's 5 there. Give me another point, the height is 5 there as well, the height of the surface we're trying to draw. And we notice that it's hard to completely see this structure in 3D from this 2D sketch, just because we're using 2 dimensions to represent 3, and this is pretty much the best we can do. What about a surface where it's the same thing, same as a constant, but the surface is at height -2? Let's draw that out. So we'll have our x, y, and z, and again, at all x, y points, the height of the surface, this is another way to say what we said on the previous page, the height of the surface is at z equals -2. So here we have to be a bit careful. We typically think of the xy plane as being at z equals 0. So z equals -2 is below, or is drawn below, the xy plane. So we simply extend the z-axis down. We don't typically draw it all out, but we recognize that there's a point below the surface here going downwards, and that the plane we're talking about in this case is going to be located at that height. And no matter what x and y coordinate I pick, I would go down to the plane and find the height there. So at a certain x and y, we'd get the coordinate of the surface, xy -2. So typically when we just give an xy coordinate, we sort of imply it's at z equals 0 just for visualization's sake. And then we add the z value when we apply the function to that coordinate, to that location in x and y. Let's break it up a little bit more. We have x, y, and z again, but in this particular function, we're going to have a plane at z equals 1 height, and we're also going to have a plane at z equals -1 height. So let's draw those 2 points on our graph here. Let's draw that in black like the last one. We would have another point down here at -1. Now the difference between, or where these two planes apply, depend on the y value, and the y value again is left to right. So imagine the y-axis continuing on this way with the origin being at this crossing point. So when y is positive, we get the value 1. And so that means, I'll try to draw it this way this time. Here we go. And again, drawing a plane is a matter of interpretation here. Try to draw it in perspective to give that three-dimensional sense, but sometimes it's hard to convey with such straight lines. But here's a plane at height 1, which would go on forever in these 3 directions here. And then we also have a plane at height -1, which occurs where y values are negative, that way. And the y values are positive as we move towards the right. So this would be 2 planes, one just above the other. And if we draw it with a straight-on view or a side view from the y and z directions, what we would have here is an open circle and a plane, and then a closed dot and a plane this way. So this would be the side view. Well, I guess technically the front view, if we were doing this looking down the x-axis. We would see a plane move off to our right and a plane move off to our left, one at height 1, one at height -1. So we can get more interesting shapes here, and I think we get a feel already that sketching these graphs is challenging, and so far we've only dealt with planes, right? There's been no curves whatsoever, so these are the most boring shapes we can imagine, and certainly not the kind of shapes we're going to be interested in studying with calculus. So here's my first reassurance to you. We are not going to ask you to sketch two variable functions. It's not going to happen. We're going to find alternate ways that you can sketch by hand, and we're going to rely on recent modern inventions, computers, to let us plot these graphs so at least we can see an association between the graph and the function that we're working with.